Hello. So let's begin one more session on infinite series. And last few lectures we had been discussing positive series, that is series of positive terms. And for today we will talk about alternating series. What is that? As the name suggests, this is a series in which the terms are alternatively positive and negative. So let's see examples. Say 1 minus half plus 1/3 minus 1/4 plus and so on. So of course we can easily see that the terms are alternatively positive and negative. And in the summation notation we can write it like this: summation n equal to 1 to infinity minus 1 to the power n minus 1 by n. So the numerical value is 1 by n for the nth term, and the sign is taken care of by minus 1 to the power n minus 1. Another example, summation n equal to 1 to infinity cos n pi by n square plus 1. Is this an alternating series? Yes, because remember that cos n pi is minus 1 to the power n. So as we put the values of n as 1, 2, 3, we will get the series as minus half plus 1 by 5 minus 1 by 10 and so on. So of course this is alternating. Now we have a very important theorem on alternating series by Leibnitz, which is basically a test of convergence. So what does it say? The alternating series summation n equal to 1 to infinity minus 1 to the power n minus 1 un is convergent if the sequence un is monotonic decreasing and limit n tends to infinity equal to 0. So we have two conditions to be tested for an alternating series to be convergent. One is the sequence un. That means this is the sequence of the positive terms is monotonically decreasing and limit un should be 0. Now it's obvious then we can conclude that if limit un is not equal to 0, the series will not be convergent. But note one thing, it's not divergent also, because your terms are alternatingly positive and negative, so the series is going to be oscillatory if limit un is not equal to 0. So let us now take up some examples to test convergence for alternating series. So the first example here is determine if the following series is convergent. What is the series? 2 minus 3 by 2 plus 4 by 3 minus 5 by 4 and so on. So how can we write this series in the summation notation? We can write it in this notation: summation minus 1 to the power n minus 1 un. What is un? Where un will be given by n plus 1 by n. You see the fourth term we have 5 by 4. The third term we have 4 by 3. So un is n plus 1 by n. Now to test by Leibnitz theorem, we have to check two things. One, that the sequence un will be monotonically decreasing and limit un should be 0. Now let us check the limit quickly first. So limit un n tends to infinity. Now what is un? N plus 1 by n. So that is nothing but 1 plus 1 by n. So now as we take n tends to infinity, 1 by n goes to 0. So this is nothing but 1. So therefore, of course, this is non-zero. And if it is non-zero, we can conclude from Leibniz theorem that the series is not convergent. And as we have already said, in this case, it is going to be oscillatory. Okay, another example. Test the convergence of the series summation n equal to 1 to infinity cos n pi by n square plus 1. We have already seen this series in the examples when we discussed alternating series, and we know that this is an alternating series because cos n pi takes the values in the form of minus 1 to the power n. So therefore, this series can be written as summation minus 1 to the power n un, where un is of course 1 by n square plus 1. So now let us check both the conditions of Leibniz theorem one by one. So in order to check whether it's monotonically increasing or decreasing, we need to look into un plus 1, which will be now 1 by n plus 1 whole square plus 1. Now, note that obviously n square plus 1 is less than n plus 1 whole square plus 1. And therefore, if we reciprocate these quantities, un is 1 by n square plus 1 will be of course greater than un plus 1, which is 1 by n plus 1 whole square plus 1. So therefore, this confirms that the sequence un is monotonically decreasing. And what is limit un? We can easily see that limit un, where un is 1 by n square plus 1, is obviously 0. So therefore now both the conditions of Leibniz theorem have been satisfied, and hence by Leibniz theorem we can conclude that the given series is convergent. With this example, we will close today's session, and in the next lecture session, we will continue with some very important concepts of conditional convergence and absolute convergence for mixed series, that means series again containing positive and negative terms. So thank you and goodbye till then.